Good morning everyone, welcome to today's worked exam answer video. Today I'm having a look at a delightful NMR / infrared / sort of bringing all of the analytical techniques together question. It is an OCR A question from the 2019 Synthesis and Analytical Techniques paper. But in terms of AQA students, you also will get questions similar to this. This sort of peak you won't get, however, but I'm sure there's plenty you will still be able to learn throughout the video. So we basically are given a range of different data, and for 6 marks we have to use all of this information to suggest one possible structure for the unknown compound and then show all of our reasoning. So the first piece of information that we've got is the elemental analysis in terms of the percentages of carbon, hydrogen and oxygen by mass, and then we're also told that the molecular ion peak was found at an MZ value of 164 on the mass spectrum. So that's going to enable us to work out the empirical formula followed by the molecular formula, and that I think is a good place for us to start. So anytime we're doing empirical formula, we're going to need we don't need to, I suppose, do it in a table, but we're going to need to know the masses, the relative atomic masses to be able to work out moles, to then be able to work out the simplest mole ratio and then convert that into whole numbers. So carbon percentage by mass is 73.17, hydrogen is 7.32, and oxygen is 19.51. And then from the periodic table, carbon's AR is 12, hydrogen's is 1, oxygen's is 16. And then I will always set it out like this because mass divided by AR gives us moles. And I'll apologise now for the noise of my cat in the background. I did pause the video and try and get him to shh, but he's on one a bit this morning. And then work out what the mole values are going to be for each of these. So I'm going to write them to 3 significant figures. So that's going to make that 6.10, 7.32, and 1.22. And then because the moles of oxygen is the smallest, I'm then going to divide all of them by 1.22, which will give me 1 mole of oxygen, 6 for hydrogen, and 5 for carbon. So the ratio is 5 to 6 to 1, and that means my empirical formula is going to be C5H6O. Now, the molecular ion peak has an MZ value of 164, so if I now work out what the MR of our empirical formula is, we can see if they're the same, or if not, by how much we're going to need to scale our empirical. So 5 lots of 12, add 6 lots of 1, which is 6, add the 16 for the oxygen, that has an MR of 82, and so because 164 is 2 lots of 82, that means the molecular formula is going to be C10H12O2. And that's a very important thing to being able to work out. Now, with a molecular formula like that, one of the first things that I thought was, oh, we don't have a lot of hydrogens for the number of carbons we have. So I was thinking we're going to need some sort of maybe cyclical structure, whether that was aromatic or not, or a number of double bonds. And they were just things that I was musing at this point when I worked through this question prior to the video. That is all we can do with that information. So next up, let's have a think about what we can learn from the infrared spectrum. Now, I would argue that there's kind of three things that we should be looking at here. Two that I think are particularly obvious that the mark scheme picks up on, and then an extra one that I think can be quite useful as well. So for this, we're going to need our data sheet. Here we are. And essentially the three peaks that I was thinking about were this one, this very broad one here, this one, and then sort of these ones sort of in this region here. So I'm going to label those as A, B and C, just for the purposes of me being able to then show you what A, B and C are going to be. So A is a very, very broad peak, and if we go down the list on the data sheet, the only one that says it's ever broad is the carboxylic acid OH peak. Now I know that that lies in the same sort of region as some of these other peaks. So for example, the C to H bond, which will also be built into that peak. Perhaps a little bit of this as well, but we know that we don't have a nitrogen within our molecular formula, so it can't be this. And then I would argue that it doesn't quite fall into this region because 3600 would be there, and the peak doesn't go anywhere near sort of the extremity of that range. So for me, peak A told me that we had the OH bond in a carboxylic acid. And how I would use this to show my reasoning is I would say that there was a peak at, and I would quote from the data sheet, that there was a peak between 2500 and 3300 centimeters to the -1. I would also comment that that says it's a broad peak, which ours definitely is. Therefore, we have an OH bond in a carboxylic acid. And as soon as we've identified that, and we know it's an OH bond in a carboxylic acid, there then has to be a C double bond O, because otherwise you can't have a carboxylic acid. That's its functional group. So coming back to the next peak, we can see we've got one just over the 1700 mark. And oh look, that's our C double bond O, which lies between 1630 and 1820. Now, in terms of these two ranges being kind of very close and overlapping slightly, simple thing to check, the peak is at least on 1700, and if not slightly more to the left, which is in the higher ranges. So a C double bond C, you might expect to see more sort of here rather than a little bit further to the left. So peak B, and again, just going to structure this in the exact same way. So we have a peak between, and then what does it say on the data sheet? 1630 to 1820 centimeters to the -1, and therefore we have a C double bond O, and then those two things together would suggest that we have a carboxylic acid group present within our unknown compound. Now, the one that isn't mentioned on the mark scheme, but I think is also important to have a think about, is in relation to the comment I made about the molecular formula. For C10H12O2, we don't really have that many hydrogens, so is it cyclical? Is it aromatic? Do we have double bonds present, like carbon-carbon double bonds outside of sort of an aromatic structure? And I was contemplating whether that peak alone here could be sort of an alkene C double bond C, but I decided that, again, because that's where 1600 would be, that it's not quite where I would expect it to be. It is kind of, in terms of like its size, the C to C alkene double bond does tend to be a bit shorter. You don't get it dropping as much in terms of the transmittance on the y-axis. But then I thought, could it be that we have sort of this going on? Because it says several peaks in the range of 1,450 to 1,650, and 1,450 is kind of here-ish, and then 1,650 here-ish, and we do have quite a few peaks in there. So I was leaning towards that telling me that perhaps we had a benzene structure. So potential for there to be several peaks between 1,450 and 1,650 centimeters to the -1. Therefore, do we have aromatic C double bond C? So is there the potential for us to have a benzene ring? And that would certainly fix the problem of having not very many hydrogens, because benzene's formula on its own is C6H6. So it obviously isn't going to account for all of the carbons. So then if we have some other things coming off of the benzene ring, then that will provide us with our remaining hydrogens. But I thought that that was quite helpful. Even though it wasn't mentioned on the mark scheme, it certainly helped me moving ahead into the NMR information. Now, in terms of the NMR information, I personally would always want to have all of the information in a more tabulated format, and there's nothing to stop you from kind of doing what I'm about to do in the table, sort of on the spectrum itself, but this is just how it works for me. So what I'm going to do is I'm going to create a bit of a table with chemical shift in one of the rows, and then I'm going to have the relative peak areas in another row. And then I'm going to have the splitting patterns in another row. And then anytime I have splitting patterns, I always then use those splitting patterns to determine how many neighbouring hydrogens there would be, and I always write that in a separate row, sort of underneath, like so. Now we've got 4 sort of different peaks, so I'm then gonna make a table for that. And a table like this can form a part of your reasoning, so long as it's clear and obvious sort of what the table is showing. And you'll see what I mean when I lay it all out, hopefully. Now the chemical shift values are going to have to be approximate because we're reading them off of the spectrum. So I took the chemical shift value for all of this on this side to be roughly sort of 7.2. That is an approximation, but we don't need to be that specific, because if we have a look at the data sheet for the hydrogen NMR chemical shifts, they're quite broad in terms of where we would expect to find a peak for hydrogens bonded to different things in different environments. So we don't need to be bang on the money. We can be, you know, precise to an extent, but it doesn't need to be the most precise thing ever. So then I did, for this peak here, I did it as 2.7 parts per million. And then I did this singlet peak at 2.4. And then I did the final peak, the doublet here, I think I did that 1.5. but it did say allow approximations for the chemical shifts in the mark scheme. So if that was 1.6, not 1.5, if that was 2.8 instead of 2.7, I think they did this one as 7.1 instead of 7.2, but they were happy with that. Now, the relative peak areas which have been given, that tells us how many hydrogens are in that environment. So there are 4 hydrogens within this environment that create this peak. There's only 1 in that environment, and there are 3 in this environment, and then there are 3 in this environment as well. So relative peak areas are the number of H atoms in the environment, which is very helpful when it comes to putting structures together. So that's what they're telling us. Now, this can be confused with splitting patterns sometimes. The splitting patterns tell us how many neighbouring hydrogens there are. So if we know how many hydrogens are in an environment and we know how many hydrogens need to be in a neighbouring environment, again, that's only useful, or is only going to be really useful in helping us to put this structure together. Now, splitting pattern wise, this mess over here, that is definitely a multiplet. And that's the bit that if you're an AQA student watching this, you would never need to ever call a peak a multiplet. That is not in your specification. And therefore, I'm not going to be able to write anything in here because multiplet is a very general term for anything above a quartet. So that's where that kind of falls down a little bit. But for the others, it doesn't, because the peak here, that represents a quartet, and you'll always see that the 2 in the middle are taller than the 2 on the outside. So that is a quartet. Then we've got our singlet, just our straight line. And then we've got the doublet at the end. Now, in terms of how many that means they have to be next to, we use the n+1 rule, where n is the number of neighbouring hydrogens, and then we add 1 to that, and that shows the splitting pattern. So I can't fill that in for the multiplet, but for the quartet, to be a quartet peak, there needs to be 3 neighbouring hydrogens, because 3 + 1 gives 4, and if we have 4, that's going to give us that quartet looking peak. So that's going to be next to 3 hydrogens. The singlet is formed because there are no neighbouring hydrogens, because 0 + 1 is 1, and yeah, we can't have next to no hydrogens and it not give us a peak at all, because there are hydrogens in that environment, and that's where the n+1 rule, I guess, is very helpful. And then a doublet, that needs to be next to 1 hydrogen, because 1 + 1 would then give us 2. So there is 1 hydrogen next door to the hydrogens in that environment. So splitting patterns tell us the number of H's on neighbouring carbons. And that in itself is really useful, because I can already see that I have this sort of inverted complementary sort of relationship with these 2 peaks here. So there is 1 hydrogen in this environment that needs to be next to 3, and there are 3 hydrogens in this environment that need to be next to 1. So I can already say that those 2 peaks show that the hydrogens in those environments are next door to each other, because we have the 3 there next to 1, and we have the 1 there that needs to be next to 3. So hopefully you can see what I'm kind of referring to there. So I therefore need to make sure in my structure at the end that I have an environment with 3 hydrogens, and on the next carbon I only have 1, and that's going to be really useful. Now, the next thing that I would be doing for the 4 peaks is trying to draw a bit of a fragment which matches the chemical shift values and brings in sort of the relative peak areas, so the number of hydrogens in the environment, and then potentially starts to think about neighbouring ones as well. Now, in terms of the order I did this, I started with the multiplet up in the sort of 7.2-ish region, and the only thing on here outside of an OH group or an NH group, that one not being relevant because we have no nitrogens in our formula. This one, we do have a carboxylic acid group, but that would only be 1 hydrogen. And here it says the relative peak area is 4. Can't have 4 hydrogens coming off of 1 oxygen. We also don't have 4 separate OH groups because we only have 2 oxygens in total. So that would suggest that this peak here is a benzene ring structure, which we kind of saw in the infrared a little bit. And that again links back to the molecular formula idea of us not having that many hydrogens. And we also knew that we were going to need to, if we did have a benzene ring, have some carbons coming off of that to make up our 10 carbons. So only having 4 hydrogens on there suggests that we've got 2 hydrogens that have been substituted for other things. But that in itself is really, really useful. So this multiplet here, what I would then draw underneath, and again this forms a part of your, I guess, reasoning, your explanation, because that lies within that range, the 7.2 for the chemical shift sits within this region here. We can then say that we've got a benzene ring that's got 4 H's on. Now, it doesn't matter where you choose to put those 4 H's, I just so happened to put them looking like that, and then I had my substituted things top and bottom. But again, the mark scheme allows you to have those 2 things substituted into any positions. But that's where that comes in. Then basically we need to repeat that, but for the other chemical shift values. Now, the next one I did was the one at 1.5, because that seemed quite nice. It had to be hydrogens on a carbon that were next to another carbon, just like a sort of alkyl chain. So that's what I then drew for this. Now, on the data sheet it just says 1H on a C, but that's just to show you that it's the H's on this carbon that would form the peak that lies within this particular region on the spectrum. We know that this environment has 3 hydrogens in it, so that is going to be a CH3 that then needs to be attached to another carbon for our R group. That's what that tells us. Then we've got these 2 peaks that both lie sort of 2.4, 2.7, around the same region, which again, there's only one thing that can be on our data sheet. Well, there's only one box it can fit into. Within there are actually 3 different things it could be. Hydrogens on a carbon next to a nitrogen. We don't have that based on our molecular formula. Hydrogens on a carbon next to a C double bond O, and that one potentially could be true, but it's not, because we know that our C double bond O is part of a carboxylic acid and that has its own separate region on the data sheet. So it can't be that. So it has to therefore be that we've got hydrogens on a carbon attached to our benzene ring. And it's going to be the same idea for both. So these are the hydrogens on carbons that form our substituent groups on here. So the way that I then drew that was that we would have to have off the benzene ring a carbon that for this environment was attached to 3 hydrogens because of the relative peak area. So that is just a CH3. And that makes sense that that is then a singlet peak, because on the next carbon, which is this one, there are no hydrogens because the CH3 is substituted for the hydrogen because it's benzene. Each carbon in the benzene ring can only be bonded to one thing in order to keep the ring of delocalized electrons. So that was then all I could think of for that. Couldn't link it to anything else. And then for the final one, we also need to have hydrogens on a carbon attached to the benzene ring. But on that carbon there, there's only one hydrogen in that environment. So we've got one H, and then we've got 2 things that will then be attached to that carbon that are not hydrogens. And this is where we can hopefully see how these 2 peaks that I kind of said are going to be made from hydrogens adjacent to each other come together, because we had this as an R group which needed to be a carbon, which is going to be the pink carbon there. So on the end of one of these lines, these bonds, I can put this blue CH3, and then I'm going to have 3 hydrogens next to 1, and I'm going to have 1 hydrogen that's next to 3. So that's going to go on there. The CH3 group's going to go on the opposite side of the benzene ring with the 4 hydrogens in the other 4 positions. So then what's going to go on here? Well, the only thing we haven't accounted for yet is our carboxylic acid functional group. So that would then be going on there. And then once we've drawn that, we can check that that fits with all of the data that we have. So start with the benzene ring, and this is where NMR is definitely like a puzzle that we're solving, kind of like an intellectual puzzle, but also like a jigsaw puzzle, because we're literally just piecing the fragments together. So those were the 4 hydrogens that gave us the multiplet peak. And then I need the CH3 that gave us the singlet peak at approximately 2.4 parts per million. And then I need the quartet hydrogen there. And then here comes the blue CH3. And it doesn't matter which side I put this on. And then the only thing that can go on the other side is our carboxylic acid functional group, which we learned from our infrared spectrum. So let's see if that works in terms of, do I have 10 carbons? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 12 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And 2 oxygens, 1, 2. So it meets the molecular formula. I've got an OH of a carboxylic acid, I've got the CO for the carboxylic acid, and I potentially had a benzene ring. All of those have been accounted for. Then I need to show that I've got 4 hydrogen environments, the purple, the green, the blue, and the pink. That the quartet and the doublet are formed from hydrogens that are adjacent to each other, and I have put those hydrogens adjacent to each other. This would be a singlet because there are no hydrogens on this carbon of the benzene ring. That would be a quartet, it's next to 3. These 3 would be your doublet because they're next to 1. Benzene ring, as we said, because that's a multiplet, that bit doesn't really work. So yeah, I think that matches exactly what we need. Now, in terms of the one possible structure, as I said, I've chosen to substitute the CH3 and the CH-CH3 Cu group opposite each other. But had I have chosen to have the CH3 in one of the adjacent positions or here, wouldn't have mattered. So we can't distinguish that from the NMR. So we could have had the CH3 in the ortho, para or meta positions, and you would have got the marks for that. Now, the only thing that I think I would need to add to this in order to make sure that I got the marks is some sort of comment about what I did with the peach, in terms of suggesting that those hydrogens were adjacent to each other. And that can be quite hard to kind of explain. But for these two peaks, I would say that we've got one hydrogen next to 3 hydrogens and 3 hydrogens next to 1 hydrogen, therefore adjacent H environments. But by connecting the fragments to each aspect of the NMR spectrum, and for drawing out on each fragment the right number of hydrogens to match the relative peak areas, that's kind of explaining all of that. So that is what I would do for the 6 marker. And I appreciate that that was quite a long video, but it was really important for me to explain sort of each of the different components of that and make sure that you could see exactly what my thinking was and how I put that together. Any questions about that, please do let me know. As always, I'm very happy to do more NMR questions from both AQA and OCR A, or any questions that you would like me to do. Okay, just let me know, keep in touch, and stay well everyone, and I hope you have a nice weekend ahead. Bye.